Hello everyone. We're going to start our discussion through this video of the transition metals and coordination compounds. So to get started, a little bit about why you might care about this. A lot of minerals that have a color are due to the types of bonds that are going on with the transition metals. For example, the color of a ruby and the color of an emerald are both due to the same exact ion. It's a chromium plus 3 ion. So you might wonder, well, how can you have such a big difference between those? And the reason is because of what other things are going on. So what is that ion bound to in the mineral? And if you have different minerals, so we have one that's mainly aluminum oxide, we get one color. If we have one that is a silicate, we get another color, but it's the chromium in each case that is giving rise to that color. So one of the things we'll be looking at in this chapter is how we get a lot of these really brilliant colors that come up in minerals and other places because of transition metals and how they bond with other things. This is something we'll also be investigating in our last in-person lab. To start with in this video, we're going to do a lot of review of the transition metals, things you should have seen a little bit of in Chemistry 1A, and then we will get into kind of introducing some of the new ideas that we need to have this understanding of transition metals to be able to fully comprehend. One of the things that we should start out by saying is that transition metals will all have very similar properties together relative to other parts of the periodic table. So the main groups, you have one particular column will have very different properties than the column next to it. Within the transition metals, all of them will be very similar in some ways. So those similarities are they will have high melting points for the most part, high densities. The hardness is usually pretty hard to somewhat moderate in some cases, and very good at conducting electricity. So those are properties that all transition metals have in common. The reason why they have these similarities is because of their valence electron configuration, just like anything else, right? That's why that is true. And in most cases, they have two valence electrons. And so having two valence electrons leads to having all of these properties. So just a review of electron configurations and how we know that they each have two. Their electron configuration is going to be this form, so ns2 n minus 1 dx. So for the first series of transition metals, that would be, so argon is the noble gas before that, 4s2 3dx. X is however far it is along in that transition metal series. And then the second one would be Kr, previous noble gas, and then 5s2 4dx. So that kind of whatever period you're in, ns2, and then period minus 1 d whatever dx. So anywhere along that, from 3 to 12 along the periodic table. For the third and fourth, we have also the f's. So we have n minus 2 f14 and then n minus 1 dx. We're not going to worry too much about the f's in this class. When we form ions from transition metals, they will generally lose their s electrons first and then their d electrons. So the ns electrons first are lost, and then the n minus 1 d electrons. That is not the same order that we put them in, right? So it's a little bit tricky in terms of figuring that out. So we'll get a little bit of review on that. This will be important because we'll be looking at bonding of transition metals And we have to know where they start in order to know how they bond. There are a couple of irregularities that we'll go ahead and mention. In this, the reason why we have these irregularities is because the S and D are often closely spaced, especially so 4S and 3D are close together, and then when you get to 5S and 4D, that gets even closer. We're just going to look at a couple in the 3D. Chromium and copper are the two, and what they have in common is they are doing basically S1 instead of S2, and they're doing it so that the D can be either halfway or all the way full. And if you think about, what those electrons are doing, mainly Pauli exclusion principle there, what you'll see is that if you have D5, each of those orbitals has one electron. That's very stable to have everything with one electron, even if 3D is a little bit higher than 4S in most cases. To have everything halfway full is more stable. Same thing with copper. Having the 3D all the way full ends up being more stable than having the 4S all the way full and the 3D not quite all the way full. So those irregularities come up usually for that reason. If there's a way to get the transition metal to have a full or half full 3D, then the S will be half full as well. So what I want to do, I want to take a minute to review this. So please pause your video, take a minute to go through and do each of these, and then we'll come back together and I'll walk us through doing each of these electron configurations. Okay, so let's go ahead and go through these. So we need to draw electron configurations for the following elements and ions. So the first one we have is iron. In order to know how to do this, we obviously will need to look at a periodic table. So let's go ahead and pull one up and see if we can make some decisions. So here we're seeing a periodic table. So iron is right here. We can see, so the previous noble gas is argon, and then we have 4s2, and then we have this 3d area, and we go 1, 2, 3, 4, 5, 6. So it would be 3d6. So let's go back to our question, and we'll write that out. So we had decided this was argon, and then 4s2, 3d6. I'm not going to go back to that periodic table for these other two, but you would be doing basically the same thing. So for titanium, we would have argon, 4s2, 3d2. Manganese, again, these are all in the fourth period, so the first transition metal series, and then 4s2, 3d5. Okay, so these we can get basically from the periodic table if you know how to interpret it. You should be able to use any periodic table to make this decision. It doesn't have to be a special one where it's showing you the 4s, what's 3d, etc. You should be able to do this with any periodic table. Now we're going to go ahead and do the ions. So for the ions, what we need to realize is we're losing electrons. So how many electrons are we losing? And which electrons are we losing first? So for the first iron, we are losing 2 electrons. We're not losing any of those core electrons, so we'll start with argon. And then we lose 4s before we lose 3d. So we'll lose both of those 4s electrons. So we will have 3d6 for that one. And then for the next iron, it's a +3. So we're losing 1 additional electron. So we can kind of start where we were on the one before, and then lose 1 more electron. So this would go from a 3d6 down to a 3d5. 5 as we lose that one additional electron. The next one we have is titanium plus 2. So we'll see what titanium is, and then we'll lose 2 electrons, again losing the 4s electrons first. That's exactly how many electrons we need to lose. So we'll have argon and then 3d2 having lost those 2s electrons. Manganese, same thing, losing 2 electrons. So we'll have argon and then 3d5. And one thing that we'll notice is that losing 2 electrons is very common because we're losing those 2s electrons. Sometimes we'll lose more than that. These two can also lose some of their d electrons. But losing 2 is often common because it's very easy to lose those s electrons. Okay, so we've gone through and done these electron configurations. You should feel comfortable doing this for any of the transition metals, both the as the element and as the ion. One thing we saw in this exercise is that we have a lot of oxidation states possible, or at least we saw for iron that we had a couple of oxidation states possible. It turns out that we have a lot of oxidation states possible for a lot of the transition metals. So they often exhibit multiple oxidation states. This is why in Chemistry 1A, when we talked about naming compounds that contain transition metals, we had to include something about what the charge was because we didn't know in any given case what that charge was going to end up being. So we're seeing a lot of variations here in possible oxidation states. We see manganese has the highest as a +7, can essentially lose all of those electrons down to the core valence electrons. And then we have other possibilities for some of these. You'll notice that kind of towards the edges, so the zinc is always a +2, scandium always a +3. Hopefully that makes sense. So, you know, if you have all of the d electrons, it's easier to pretty much keep those and just lose the s. Easier to maybe here lose all 3. And then for most of them, the +2 is very common, and we don't have a lot of +1, so copper is kind of the exception there. And if you think about what we had for that electron configuration, that's the one that has 4s1 3d10. So losing that s1 is fairly easy for it to do. You don't have to memorize these. Just be aware that there are a lot of possibilities. You should be able to kind of understand how we get to 1. So like we looked at the iron, why is a +2 and a +3? Why are those the most common? That should make sense based on your understanding of electron configurations. But you don't have to memorize these. So that's a little bit of review of things you would have seen, should have seen in Chemistry 1A that will be applicable to what we're doing next. So the charge, understanding the electron configuration and the charge of those metal ions is very important to what we'll be looking at next and how they bond. We need to know where those electrons are to determine some of the things going on in this kind of bonding we'll be looking at next. So we'll be talking about what are called complex ions. In a complex ion, we have a central metal ion bound to some other things that we call ligands, and we've been hinting at this all semester. We've seen it come up a few places in the lab, this idea of a ligand, and it's basically something that's donating an electron pair to the metal ion to help stabilize the positive charge, whatever that charge is on those metal ions. And these form, as the name suggests, a very complex species that we have a lot of things we can talk about in terms of understanding what is going on with these. So that is where we will pick up when we get to class. Next time we'll discuss complex ions, what they are, how to understand them, and how eventually that leads to having different colors for different minerals.